There is a structure in space so large it should not exist. Scientists have a hard limit, a boundary set by the age of the universe itself, that says nothing this big could have formed this early. And yet, the James Webb Space Telescope just found one. Stay with me, because this gets stranger. Because if this thing is real, it does not just break a record. It may break our entire model of how the universe was built. Somewhere in a quiet lab, surrounded by monitors and data streams, a team of astronomers was doing what they do most nights: reviewing, checking, looking for signals in the noise. What they found was not what anyone was expecting. The James Webb Space Telescope had sent back data from one of its deep observation sessions, a long stare into a region of space that looks, to the naked eye, completely empty. But with JWST, the empty space is rarely actually empty. And this time, buried inside the data, there was a signal. A cluster of objects, densely packed, gravitationally linked, sitting at a redshift so high that, when scientists calculated its distance, it placed this structure in the first few 100 million years after the Big Bang. Let that settle for a moment. The universe is roughly 13.8 billion years old. This structure appears to exist from an era scientists call the Cosmic Dawn, a time when the universe had barely cooled from its initial expansion. The first stars were only just beginning to switch on. The first atoms of hydrogen and helium were only just starting to gather under gravity. Life, planets, even complex chemistry. None of it existed yet. The universe was still in its infancy. And inside that infancy, so something enormous had apparently already formed. To understand why this is so unusual, we need to understand the scale problem. The structure detected is not a single galaxy. It is not even a small group of galaxies. Based on the data, researchers estimate it could be spanning hundreds of millions of light years. For comparison, our own Milky Way galaxy is about 100,000 light years across. The distance between the Milky Way and our nearest large galactic neighbor, Andromeda, is roughly 2.5 million light years. The structure JWST flagged is potentially far larger than anything in our local cosmic neighborhood, and it was supposedly all in place when the universe was less than 1 billion years old. This is not a small anomaly. This is not an error margin problem. If confirmed, yet this is the kind of discovery that forces entire textbooks to be rewritten. Right now, before we go any deeper, what do you think is really happening here? Does the universe have secrets it has been hiding from us? Drop your thoughts in the comments. I read every single one. The detection was made using JWST's NIRCam instrument, the near-infrared camera. This instrument is one of the most sensitive infrared detectors ever built and placed in space. It can capture light from objects so far away that the light itself has been traveling since nearly the beginning of time. When light travels across billions of light years of expanding space, it gets stretched. Short, high-energy wavelengths stretch into longer, lower-energy infrared wavelengths. This process is called redshift, and the further away an object is, the more its light shifts toward red and beyond, into the infrared range. NIRCam is specifically designed to capture this ancient, stretched light. What researchers flagged was a concentration of infrared sources, galaxy candidates, arranged in a spatial pattern that suggested they were not scattered randomly. They appeared gravitationally connected. The arrangement hinted at a protocluster, or possibly something even larger, a segment of what cosmologists call the cosmic web, the vast filamentary structure that connects matter across the universe at the largest scales. When the team ran spectroscopic analysis, a technique that breaks light into its component wavelengths to extract detailed information about an object's distance, composition, and velocity, the numbers came back consistent. This was not a processing artifact, and this was not a smeared signal from something closer. The data pointed to a genuinely distant, genuinely old, genuinely massive structure. They checked the data again. Then again. The signal held. One researcher, according to reports circulating in the community, described the initial reaction simply. They said it looked wrong. Not wrong as in a mistake. Wrong as in something the model did not predict. There is a difference. And in science, when something looks wrong in that second way, it usually means something important is happening. But before we understand why this breaks the model, we need to understand the model it is breaking, because the story of how scientists think the universe grew is itself a remarkable one. And it is only once you know that story that the full weight of this discovery becomes clear. To understand what JWST has found, you need to understand the blueprint, the plan the universe was supposed to follow, because there is one. And it is not just a theory someone wrote on a whiteboard. It is a model built over decades, tested thousands of times, supported by mountains of observation. It is called the Lambda CDM model, and it is the closest thing cosmology has to a master description of how everything came to be. Lambda CDM stands for lambda cold dark matter. Lambda represents dark energy, the mysterious force that drives the universe's accelerating expansion. CDM refers to cold dark matter, the invisible mass that makes up roughly 27% of the universe and acts as the gravitational scaffolding on which all visible structure forms. Together, these two ingredients, along with ordinary matter, which makes up only about 5% of everything, define the recipe the universe has been following since the Big Bang. According to this model, the universe was born nearly perfectly smooth. Not perfectly, but almost. If you could have taken a snapshot of the universe just a few 100,000 years after the Big Bang, it would have looked almost uniform in every direction. Matter was spread with extraordinary evenness, but not absolute evenness. There were fluctuations, tiny wrinkles in density, smaller than 1 part in 100,000. These wrinkles are real. We can see their ancient imprint today in the cosmic microwave background, the faint glow of radiation left over from the early universe, mapped in extraordinary detail by missions like ESA's Planck satellite. Those tiny wrinkles were the seeds. Gravity did the rest. Over time, and this part is critical, over a very long time, gravity began pulling matter toward those slightly denser patches. Gas clouds slowly collapsed. The first stars ignited. Those early stars exploded as supernovae, seeding the surrounding gas with heavier elements. New generations of stars formed, galaxies assembled. And then, over hundreds of millions of years more, galaxies themselves began clustering together, drawn by mutual gravity into groups, then clusters, then the vast filaments and walls of the cosmic web. The key word in all of that is slowly. Structure formation in the Lambda CDM model has a natural speed. It is governed by how quickly gravity can act, how quickly matter can cool, and how quickly early fluctuations can amplify. Simulations built by institutions like the Max Planck Institute for Astrophysics, EIMIT's Kavli Institute, and the Virgo Consortium, simulations that model the evolution of billions of particles across billions of years, consistently show the same thing. Large-scale structures take time. There is a minimum growth timescale. You cannot rush it. The physics does not allow it. Think of it this way. Imagine you are trying to build a mountain using only natural forces, erosion, tectonic uplift, the slow accumulation of material. There is a minimum speed at which that process can work. You cannot have a mountain appear in a day, no matter how much raw material is available. The same logic applies to cosmic structures. Gravity works fast at small scales, but assembling something truly enormous requires time for material to travel, accumulate, and stabilize. This is not a guess. It is mathematics backed by decades of successful predictions. The Lambda CDM model has correctly predicted the number of galaxy clusters at various distances. It has correctly predicted the distribution of cosmic Webb filaments. It has correctly predicted the clustering patterns of galaxies across cosmic time. It works. Remarkably well, in fact. Which is exactly why this new structure is so disquieting. The structure JWST detected exists at a point in the universe's history when, according to every simulation we trust, only small, scattered proto-galaxies and the earliest large-scale filaments should be present. The ingredients for something this massive should not have had time to gather. The gravitational processes that build structures of this scale should not have run long enough. It is as if you watched a construction site for a week and then came back to find a completed skyscraper. when the physics of the materials said it should have taken 3 years. And this is not the first time JWST has handed cosmologists this kind of puzzle. Since becoming operational in 2022, the telescope has repeatedly detected galaxies that are more massive, more luminous, and more structurally mature than the lambda-CDM model predicts at those redshifts. This new structure is not an isolated oddity. It is part of a growing pattern. So either the universe found a shortcut our models do not include, or our models are missing something more fundamental than anyone previously thought. And what JWST actually saw, in technical detail, makes the puzzle even more striking. The James Webb Space Telescope is not an ordinary instrument. It was designed over more than 2 decades, built by NASA in collaboration with the European Space Agency and the Canadian Space Agency, and launched on Christmas Day 2021. Its journey to operational status took months, a careful unfolding of its 6.5-meter gold-plated segmented mirror, a delicate deployment of its sunshield, and a long process of calibration and alignment so precise that engineers had to account for the thermal expansion of individual mirror segments. Its final home is not in orbit around Earth. It sits at what is called the second Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth, on the side away from the Sun. At this position, the telescope can maintain a stable temperature of around -233 degrees Celsius, cold enough to detect the faintest infrared heat signatures from the most distant objects in the observable universe. And that sensitivity, that extraordinary cold eye sensitivity to infrared light, is what makes this discovery possible. Here is the physics. When an object in the universe is very far away, it is not just distant in space. Because the universe has been expanding since the Big Bang, looking far away means looking back in time. Light from an object 13 billion light-years away left that object 13 billion years ago. By the time it reaches us, the expansion of space has stretched that light enormously. What began as ultraviolet or visible wavelengths has been stretched all the way into the infrared range. To detect it, you need an infrared telescope, a sensitive one. JWST is the most sensitive infrared space telescope humanity has ever built. Its NIRCam instrument, near-infrared camera, detects wavelengths between 0.6 and 5 microns. To calibrate that, visible light sits between roughly 0.4 and 0.7 microns. JWST sees just past the edge of what human eyes can detect, and then far beyond it. This allows it to observe galaxies whose light has been redshifted by the universe's expansion into ranges that previous telescopes like Hubble could not reach. Objects at redshift values above 10, meaning their light has been stretched by more than a factor of 11, are now accessible to JWST in a way they simply were not before. The structure in question sits at a redshift that places it within the first billion years of cosmic history. Researchers identified it through a combination of photometric analysis, measuring brightness at multiple infrared wavelengths to estimate redshift, and, in key cases, spectroscopic follow-up. Spectroscopy breaks incoming light into its component wavelengths, creating a signature that acts like a fingerprint. Known spectral lines, the characteristic emissions and absorptions of hydrogen, oxygen, carbon, appear at predictable wavelengths when adjusted for redshift. By measuring where those lines appear in the spectrum, scientists can calculate distance with high precision. What the data showed was a set of galaxy candidates, some confirmed, some still awaiting final spectroscopic verification, arranged in a spatial pattern consistent with gravitational association. They were not randomly scattered across the field of view, they were clustered. The clustering statistics suggested a real physical connection, not a line-of-sight coincidence. Some researchers describe the structure as a possible protocluster, a region that will eventually collapse and form a massive galaxy cluster, or as a segment of a large-scale filament, one of the thread-like structures that form the backbone of the cosmic web. Distinguishing between these possibilities requires additional data, but both interpretations point to the same conclusion. Something very large existed very early. One additional tool helped sharpen the image: gravitational lensing. When a massive object sits between Earth and something even further away, its gravity bends the light from the background object, acting like a natural magnifying glass. JWST is exceptionally good at exploiting this effect. Some of the galaxy candidates in this structure were identified in part because lensed arcs and distortions in nearby fields pointed to a concentrated mass behind them. This is not just useful for seeing further, it helps confirm that the mass is real and significant. The scientific community's response has been cautious but serious. At these distances, confirmation is a multi-step process. It requires multiple independent observations, cross-referencing with data from complementary instruments like ALMA, the Atacama Large Millimeter Array in Chile, and rigorous statistical analysis to rule out false positives, projection effects, and instrument artifacts. That process is underway. Peer review is ongoing, but the initial signal is strong enough that the result has been taken seriously at the highest levels of the field. If you are starting to see how strange this is, if you are sensing that this might be something genuinely important, subscribe to this channel right now. Because what comes next does not just question this one structure. It questions the foundations of how we think the entire universe was assembled. And when researchers modeled what they saw against known physics, when they ran the numbers and asked the fundamental question of whether this structure could have formed within the time available, the answer was not what anyone expected. In science, when an observation does not fit the model, there are two possibilities. The observation is wrong, or the model is incomplete. In this case, researchers have been thorough in ruling out observational error. The signal is real. The distance estimate is well-founded. The structure, as far as the data can tell us, exists. So the model must be incomplete. The question is, where is the gap? And that question has generated serious, substantive responses from three different directions. These are not fringe ideas. These are hypotheses being actively explored by researchers at some of the world's leading institutions. Each one points to a different kind of missing physics. And each one, if correct, would require a revision to our understanding of the early universe. The first explanation involves dark matter. Specifically, the possibility that the distribution of dark matter in the early universe was less uniform than the standard model assumes. In the lambda CDM model, dark matter clumps gradually under gravity and ordinary matter follows. But some researchers, including groups at the University of California, Berkeley, and the Perimeter Institute in Canada, have explored scenarios where certain regions of the early universe had unusually high concentrations of dark matter from the very beginning. Not because of random fluctuation alone, but because of additional physical processes operating during or immediately after inflation. If particular regions started with significantly more dark matter than average, gravity in those regions would have acted faster and more powerfully. Ordinary matter falling into those dark matter wells would have assembled into galaxies and galaxy clusters at an accelerated rate. The effective timescale for structure formation would compress dramatically. Under the right initial conditions, something that should have taken 2 billion years to build might have assembled in a few 100 million. This idea is not settled, but it is physically coherent, and the JWST data is the kind of evidence that pushes it from speculative to testable. The second explanation is more radical. It involves primordial black holes. Primordial black holes are a class of black holes hypothesized to have formed not from the collapse of stars, but directly from the extreme density fluctuations of the very early universe. In the first fractions of a second after the Big Bang. This was before any stars existed, before any galaxies, before anything we would recognize as structure. If density fluctuations in the primordial plasma were extreme enough in certain regions, those regions could have collapsed directly into black holes. The idea has been around for decades, proposed originally by Stephen Hawking and others in the 1970s. But recent JWST observations have given it new momentum. If primordial black holes existed in the early universe, they would have acted as gravitational anchors, dense, fixed points around which gas and dust could accumulate rapidly. They would effectively provide a head start for structure formation, bypassing the slow, bottom-up process that standard theory describes. Several papers published in the wake of early JWST results, including work drawing on data from the Cosmic Evolution Early Release Science Survey, known as SEERS, have argued that the abundance and early formation of certain galaxies, JWST has found, is more consistent with scenarios involving primordial black holes than with the standard model alone. This new structure adds further weight to that argument. The third explanation operates at the most fundamental level of all. It suggests that our model of cosmic inflation, the period of extraordinarily rapid expansion believed to have occurred in the first fraction of a second after the Big Bang, may need to be revised. Inflation, in its standard form, is thought to have smoothed the universe almost perfectly, stretching any initial irregularities to scales far beyond what we can observe. The tiny fluctuations that remained, the seeds of structure, are assumed to follow a nearly scale-invariant distribution, meaning their amplitude does not vary dramatically with size. This is one of inflation's key predictions, and it has been tested against the cosmic microwave background with remarkable precision. But some inflation models, particularly those involving multiple fields or non-standard energy potentials, predict deviations from this smooth distribution. They allow for regions where the primordial power spectrum was significantly enhanced on certain scales, producing denser than expected seeds for structure formation. If inflation generated a bump in the power spectrum at the relevant scales, it could explain why we see structures in the early universe that appear too large, too well-formed, and too numerous to fit the standard prediction. Researchers at institutions including Princeton, Cambridge, and the Kavli Institute for Cosmological Physics at the University of Chicago are actively exploring this class of models. The JWST data, both from this structure and from the broader pattern of early galaxy formation, is providing exactly the kind of high redshift constraints these models need to be tested against. All three theories remain open. None has been confirmed. None has been ruled out. What is clear is that the JWST data is forcing the field to take all of them more seriously than the pre-JWST generation of observations required. The telescope has not just found anomalies. It has found anomalies at a rate and consistency that suggests a systemic gap, something the standard model is genuinely missing. Think about this for a moment. Everything you have ever seen in an astronomy textbook, every image of the night sky, every diagram of the cosmic web, all of it was drawn using a model that this telescope is now questioning. The universe you think you know may have a different origin story than the one you were taught. That is not a dramatic claim. That is what the data is beginning to suggest. But there is a fourth possibility, one that most scientists are reluctant to say out loud. Not because it is unreasonable, but because of what it would mean if it turned out to be true. Science has a long and instructive history of moments like this one. Moments when an observation arrives that does not fit, when the numbers do not add up, when the model, which was working perfectly yesterday, suddenly has a crack in it that no one can patch cleanly. These moments tend to come quietly, not with announcements, not with fanfare. They come in the form of data that keeps coming back the same way no matter how many times you check it. They come from instruments that are too precise to be dismissed. They come from patterns that repeat across multiple, independent observations. And they come from the simple, uncomfortable fact that the universe does not care what our models say it should be doing. The structure JWST has detected is one of these moments. But it is not operating alone. Since the telescope began its science operations in 2022, it has delivered a cascade of surprises that, taken individually, might each have a conventional explanation. But taken together, they are beginning to form a picture. A picture that the early universe, the universe in its first billion years, was far more active, far more structured, and far more evolved than the lambda CDM model predicted it would be. In the first year of JWST observations, papers began appearing that described galaxies at high redshift with stellar masses, the total mass of all the stars in a galaxy, that exceeded what the standard model said could have assembled in the available time. One study, led by researchers at the University of Copenhagen using data from the JWST-CEERS program, identified several galaxy candidates at redshifts between 7 and 10 that appeared to contain more stellar mass than entire catalogs of simulated galaxies produced by the illustrious TNG project, one of the most sophisticated cosmological simulations ever run. The paper's lead author described the finding as a challenge to our understanding, not a minor one. Then came reports of galaxies with disk structures, the kind of flat, rotating, I-organized disk you see in spiral galaxies like our own Milky Way, at redshifts where only irregular, turbulent young galaxies were expected. Order where there should have been chaos, maturity where there should have been infancy, and now this structure. A massive, extended, gravitationally connected arrangement of galaxies at the very edge of the observable universe in time. Each finding by itself is a puzzle piece. But the puzzle pieces are starting to show the outline of a picture. And the picture suggests that something in the very early universe, either in the conditions set by inflation, or in the behavior of dark matter, or in physics we have not yet identified, was creating structure faster and more efficiently than our models capture. The implications are not small, where the lambda CDM model is not just a description of how galaxies form. It is the framework that underpins our understanding of dark matter, dark energy, the age and geometry of the universe, the origin of cosmic structure at every scale, and ultimately the question of how we came to exist in a universe with planets, stars, and the conditions for life. If the model needs revision at the level that JWST is suggesting, the revision will not be a minor adjustment to a parameter. It will be a genuine expansion of the underlying physics. This has happened before. In the late 1990s, two independent teams studying the brightness of distant Type 1a supernovae, the Supernova Cosmology Project and the High Z Supernova Search Team, found that the universe was not slowing down in its expansion as gravity alone would predict. It was speeding up. Yet that observation required the introduction of an entirely new ingredient: dark energy, lambda, in the lambda CDM model. An ingredient that makes up roughly 68% of the universe's total energy content, and whose nature we still do not fully understand. The observation was uncomfortable. The revision was necessary. The physics got bigger. JWST may be doing the same thing to the CDM part of the model. Institutions like NASA, ESA, and the Max Planck Institute are not treating this as a peripheral issue. Follow-up observation programs have been prioritized. JWST's time is finite and expensive, and it is being directed toward these early, anomalous structures precisely because the scientific community recognizes the potential significance. Additional spectroscopic confirmation campaigns are underway, in coordination with ground-based observatories, including the Very Large Telescope in Chile and the Keck Observatory in Hawaii, is being used to supplement and verify JWST data at wavelengths the Space Telescope does not cover. And all of this is happening while JWST is still in the early years of its operational life. The telescope is designed to operate for at least 10 years, possibly 20. The first few years of data have already produced more surprises per observation than almost any instrument in the history of astronomy. What will a decade of observations reveal? There is a philosophical dimension to this that deserves a moment of quiet reflection. Humans have been looking at the sky for as long as we have been human. For most of that time, we had no way of knowing what we were seeing, only that it was vast and old, and beyond our reach. Over the last century, we built the instruments and the mathematics to actually understand it, to measure the distances, to reconstruct the history, to develop a coherent, testable account of how everything came to be. That account, the lambda CDM model, the Big Bang cosmology, the story of cosmic evolution, is one of the greatest intellectual achievements in human history. It is not wrong, but it may be incomplete. And there is something remarkable about the fact that we have now built an instrument sensitive enough to find the places where our best story breaks down. Science does not panic when that happens. It recalibrates. It asks better questions. It builds more precise instruments. It goes back to the data. And slowly, patiently, it assembles a more complete picture. The universe handed us this structure. We do not yet know which picture it belongs to. But we are looking, with the sharpest eyes humanity has ever pointed at the sky. Because this discovery does not stand alone. JWST has been building a pattern, observation by observation, anomaly by anomaly, that is beginning to point towards something bigger than any single finding. In the next video, we look at every major anomaly JWST has delivered since 2022. Lay them out side by side, and ask the question that the data is beginning to force us to ask. Is the early universe telling us something about physics we do not yet have the language to describe? That video is already made. It is waiting for you.